everyone. This is my Emergent Reverb Generator, which is my final project. And what it does is on the click of a bang, depending on the settings you've set, it will procedurally generate a matrix and the reflection orders or the tap out times of the matrix for a feedback delay network based reverb. So first, I'm going to walk through the technical of how this is working with all these objects, and then we're going to go into presentation mode and we're going to play around with it a little bit. So before we generate a reverb, what you need to know is that there are two parameters that control the character of the reverb generated: feedback and early or late reflections. So feedback is what determines how intense the multiplication coefficients of the matrix are, which means how intense the feedback of the actual delay lines will be. So if I turn this way down and I generate, you can see that there is a lot of values that are close together in their value for the coefficients. So as you can see, there's not a lot of like long ringing out or a lot of intense feedback with that. This is also another parameter that affects something similar, which is the early or late reflections. If I turn this down, the reflections will be a lot earlier, and if I turn it up, they will range a lot more and tend to be a lot later as well. So these are both parameters that control the generated reverbs. Great. So now that you know that, let's figure out what happens when you generate a reverb. Okay, so when I click this button, you can see that these values here and these values here, all of this gets seemingly randomized. Now, I will tell you it's not completely random. There is actually a few different types of objects being used to randomize this in a way that's not random in nature, but allows you to have a lot of customization over what these levels do. So when we generate a reverb, a wireless signal is sent out here and here. Also a few other places, but that's not important. So here, this is what fills in and generates the matrix values. This is routed to here. And so what this does is this creates all of our necessary row and column values, or column and row values, and then assigns a coefficient to those values using what's called the drunk object. This is the quasi-random method that I was referring to earlier. So what this does is this performs what's called a drunken walk, wherein the values are kind of adjacent and they leap to the next value within a certain range. So as you can see, it's not sporadically scattered, but it's kind of following what's called a drunken walk. So I use this logic for the values of the matrix because I kind of wanted adjacent values and similar values to kind of be clumped up in the matrix, because that is a pattern that's observed with these optimal reverb matrices. So these are actually presets I made that are optimal matrices for feedback that don't result in any unwanted ringing out. So if this value is increased using feedback, that causes these values to clip between 0 and 10. So the range of each of these is 0 and 10. So if this is really high, then a lot of the values will clip out at 10 or clip out on the lower threshold at 0. So this results in a lot of intense feedback. Hence, this is already feeding back a lot. So you don't want to do that, really. For this, though, this is a lot more stable because these values tend to be closer to each other. Great. So now this gets filled in, but what about this? So this is where this knob comes in, because it determines the range of these values, which aren't actually the tap out times, but instead these are the indices that get mapped to the exact tap out times. So I've done this because I wanted the tap out times to get automatically quantized to a prime number, because prime numbers are optimal for delay times. So that's what I've done here, and these get assigned to each of these tap outs. So how is the matrix working? Well, actually, there's a special object in Max called the matrix tilde object, and it handles the multiplication of all these tap out delay lines by itself. So I don't have to worry about routing every single one to every single other one. There is a lot of routing here, but it just goes to the matrix object and just does its recursion, and then it goes on its way out. After it comes out of the matrix, it goes into this attenuator object that I've made, which attenuates each delay line by a scaled amount. So what do I mean by scaled amount? Is actually, depending on how high your feedback is set, it will tend to attenuate it lower. So I have this feedback all the way up. It does 0.6. If I have it all the way down, it's going to be 0.707, which is actually a special number. It's for the attenuation factor of -3 dB. And I tend to find that it was actually around the point where it was about the minimum attenuation I could have before things started becoming unstable. So that's why I decided on those numbers for that scaling. So those get scaled to the attenuation of every single delay line automatically. And then we have the summing of all the signals. So when they're summed, they get sent to a one-pole filter at 12K hertz to roll off a lot of the unwanted high artifacts and smooth them out. And we also have a cut at around 160 hertz, just for that. Also, we also don't want the super low frequencies to be getting in our way. Then I have tan H, which is a special saturation processing thing, which helps a lot with the smooth sound and just makes it sound better. Then the dry and wet signals are summed according to the user's set wet and dry level, and it comes out the output. So I'm actually using this in conjunction with my custom amp sim that I've made, because I want to show this on guitar like I did in that first clip. So I'm going to show a few of these settings that are optimal for the matrix. And I'm also going to generate a few just to see what I can get. So here's what a few of them sound like. All right, thank you guys for listening and watching.